Afternoon. Today we are going to look at the first lesson in a unit called Logarithmic and Exponential Functions. First little bit of today, we're going to go over some review of grade 9 math with exponents. And then I'm going to use those exponential laws or laws of exponents to solve equations where you have a variable within the exponent along the lines of 3x equals 27. So those are the basic equations that we're going to be working with today. Now, to do that, we need to just remember how we use our laws of exponents. I'm just going to have to get a mouse. Now again, these are not new. These are first covered in grade 9 math and dealt with in grade 10 also. If you have x to the power of n times x to the power of n, so x to the power of 3 times x to the power of 2, your product of those two numbers is you add the exponent, so x to the power of m plus n. Again, the proof can be dealt with fairly simply. Here's our x to the 3. Multiply that by x to the 2. And you can see that we're going to end up with x to the 5. A similar, well, that's not really a proof, but that's an example of it. We can do the same thing here if we're dividing x to the power of n divided by x to the power of n. We have the x to the power of x, or m minus x. Here's our x cubed over x squared. We end up crossing that off. If we take some number raised to another number, so x to the power of m, all raised to the power of m, n I should say, we have the product of those two numbers. Again, we can think about this as x cubed squared, and we can see our answer is x to the 6. We have 6 x's. These are not so much, or these are just different ways of writing these. We have x times y to the power of m. Well, that exponent is applied to everything within that bracket. So that can also be written as x to the power of m at times y to the power of m. And we can go backwards this way, and we do that quite a bit. And finally, with our quotient, again, the exponent applies to both in that, or can be written in that form. I tend to go from the right-hand side to the left-hand side, but we'll do that quite regular. Now, this one here, I don't know why they don't teach it in grade 9 anymore, but we first showed it to you in grade 10. When you have a negative exponent, so in this case, x to the power of -1, what that is telling us is that is the reciprocal of whatever's there. So x to the power of -2 would be x to the power of 1 over x to the power of 2. We're going to deal with the reciprocal of that. A rational exponent where you have a fraction in the or as the exponent, or a decimal as the exponent, you write it as a fraction. We have two ways of writing this. We can write this as we can write this as x to the power of m, and then the nth root of that one there. So if it's 1/2, we can write it as the square root of x. If it's 3/2, we can write it as the square root of x cubed, etc. Or we can also write it with that power of n outside the radical sign. And again, these are not difficult things for us. Sometimes they're difficult for us to remember, but we've used these extensively in the last 2 years. and we'll continue to use them extensively as we go through math. Now, we're just going to simplify using our laws of exponents. We're going to multiply 4 by 2, which is 8. X cubed times x to the negative 4 would be x to the power of 3 plus negative 4. We would have y to the 1 plus 2. So what we end up here is 8x to the negative 1 y cubed. And if I want to write these with only positive exponents, I would have 8y cubed over x because of that negative exponent here. In this situation, I'm going to deal with the negative first. We can do it in multiple different ways, but I'm going to deal with the negative first. It's going to be 1 over what's inside the brackets, all raised to the power of 3. And then I'm going to apply that cube to everything inside that bracket. We have 3 cubed is 27, x cubed is x to the 6, y cubed is y to the 9. Again, there are a couple different ways of working through that, but that's generally one of them. Again, here, 24 over negative 4, those are just numbers. I'll write that as negative 6. I've got m to the 5 over m to the 4. I've got p to the negative 3 over p squared, so that would be p to the negative 3 minus 2. And I've got q 4 minus negative 2. Tidying this up, we end up with negative 6, m to the 1, p to the negative 5, and q 6, which is a perfectly acceptable answer. I'm just going to write this with a positive exponent. So the negative 6, before I finish this off, sometimes it is only the negative exponent. Sometimes we make mistakes. So that negative means it's a reciprocal. No, it means it's a negative number. It's a negative 6. It's 6 to the left of our 0 on our number line. Is a negative exponent, that's when we take the reciprocal. So we have 6m q to the 6 over p to the negative 5. Simplifying stuff that we've done quite a bit in grade 10. What this now allows us to do, without use of a calculator, we can figure out all these numbers. If we break these down, I'll deal with the negative first. I happen to like that way. There's no problem cubing it first. And 2 to the power of 3. So 2 to the negative 3 is equal to 1/8. What I could do here, I could write this 81 to the 4th and then take the cube root of it. Or I could take the cube root of 81 and raise it to the power of, sorry, not the cube root, I got that messed up. The 4th root of 81 cubed, or the 4th root of 81 all cubed. Well, I could do both, but I do not want to multiply 81 by 81 by 81. So while this is true, I'm just going to ignore it. But what times itself? 4 times gets you to 81. That is 3. So this entire thing in brackets simplifies to 3 and then 27. I always do the roots first. Makes life so much easier because it gets numbers smaller, and then I can work with in my head with numbers that are smaller. Now, 25 to the 0. This is our definition of a 0 exponent. Any number to the power of 0 is 1. Okay? That is our definition of a 0 exponent. 16 to the power of negative 1/2. Okay, I can write that as 16 to the power of 1/2 to the negative 1, or I could take the negative 1 first. We're talking about the square root of 16 to the negative 1, or to the negative 1, 1/4. So I don't care in which order. I did this one with using the negative first, and that one I do with the negative second. It doesn't really matter. Now we are going to start to look at how do we use these exponent laws to help us solve exponential equations. What is an exponential equation? An exponential equation is something that has a variable in the exponent. So this is not an exponential equation. Well, sorry, this is an exponential equation. Sorry, where am I? I'll just go to another page. This is an exponential equation. Sorry, these are not exponential equations because they don't have, the exponent is a number. This is a variable. So that is just a basic equation. These are exponential equations. You've got the unknown within the exponent. And we really have never talked about solving these equations before. We've talked about linear, quadratic, cubic equations this year. Last year we talked about solving rational equations and radical equations, but never with the unknown in the exponent. So the first thing that we want to look at is, can I write something like 16 to the power of 4x as base 2? Okay. Well, so basically I want to write that as 2 to the power of something, is what I'm asking. What it goes here that's going to be equivalent to 16 to the 4x. Okay. So we have to basically, we're going to leave that 4x, we're going to leave it alone for now. We're going to deal with the 16. Well, 16 is a power of 2. We can write 16 as 2 to the 4th. So replacing the 16 with 2 to the power of 4, and then using our exponential laws, 2 to the power of 4x to the power, or sorry, 2 to the power of 4 to the power of 4x. You end up with, you multiply those two terms together. So 2 to the power of 16 is equal to 16 to the power of 4x. Okay. And the fact that it ended up being 16 is just a coincidence in this case. We're going to basically work with those things and reduce them where possible. So I want to write 9 to the power of 2x as 3 to the power of some number. That's what I mean by writing as base 3. Well, 9 is 3 squared. And I'll just keep that. So I'm going to replace the 9 with the 3 squared. 2 times 2, so 3 to the power of 4. 4x is the same as 9 to the power of 2x. 125 to base 5. 5 cubed is 125. Now we're going to multiply the two exponents. We have a power of a power, so we'll multiply the powers together. What I've got written there, 5 to the power of 3 times 2 minus x, is a perfectly acceptable answer. We may want to expand that out. I don't know. It depends upon the question. So both of those answers on that line are perfectly acceptable value. 8 times 16 to the power of x. We want to write it as one term, 2 to the power of some exponent. 8 can be written as 2 cubed. 16 can be written as 2 to the power of 4. Now we're at 2 cubed times 2 to the power of 4x. We have the same base now. We could not simplify this with those guys because they don't have the same base. We have 8 to the 1 times 16 to the power of x. We now have the same base. Now we're going to add those exponents together, multiplying exponential expressions with the same base, or if we just add the exponents. Multiplying exponential equations with different bases cannot happen until you get them to the same base. We want to write this guy as base 2. Okay, well, let's just work with the 512 to the power of 3x. So I'm going to have 512 can be written as 2 to the 9, and that's still raised to the power of 3x. Work this way, I'm running out of room. So I have 1 to the power of 1 over 2 to the 27x. Now, we're close. If I wanted base 1/2, I could do it there. But I want it base 2, so I got to deal with this fraction. So 2 to the power of negative 27 over x. Now, this guy here, 16 and 3 don't really work. 81 and 2 don't work. But if I flip that, if I start writing this as 81 over 16 to the power of negative 1, so that there will go back to that guy. And then this sticks around, the x plus 5. We haven't done anything to it. I've replaced 16 over 81 with 81 over 16 to the power of negative 1. Now, 81 to the power of, 3 to the power of 4 is 81. 2 to the power of 4 is 16. So we can write this guy in the middle as 3 to the 4 over 2 to the 4, all raised to the power of negative 1, all raised to the power of x plus 5. And quite often I would be skipping steps here, but now here, 3 to the 4 over 2 to the 4 can be written as 3 over 2 to the 4. And still raised to the power of negative 1, still raised to the power of x plus 5. So we are just going to multiply that out. 3 over 2 to the power of 4 times negative 1 times x plus 5. Tidy this up, negative 3 over 2 to the power of negative 4 x plus 5. Or negative 4x minus 20 if you wanted to expand. So that's, I'm going to skip this step for a minute. That is what we're going to use to solve certain types of exponential equations. Okay, so remember, an exponential equation is one where the variable is in the exponent. When we talk about quadratic equations, the exponent is 2, or the highest exponent is 2. If I'm talking about cubic equations, the highest exponent in that guy is squared. A radical would be something like the square root of x plus 5 is equal to 0, where you have a radical sign. A rational function is a polynomial over a polynomial equal to something. Those are all different ones. The exponential equation is where the variable is in the exponent, and this is that one here. Now, this only works, this method only works in certain situations. Okay, so in this case, these guys are all can be written as powers of 2. Okay, now I don't particularly like this 4. I find an easy way to get rid of that 4 is divide both sides by 2. Okay, so I divide both, I guess I divide by 4, not 2. Oh, I said 2. Now, here we have 2 to the 1 is equal to 2 to the power of x plus 3. We have the same base. These guys are the same. Well, the only way that the left side of the equation can be equal to the right side of the equation is if the exponent on the left side of the equation is equal to the exponent on the right side of the equation. It's not that we're dropping the 2's. We're making the understanding. The 2's are constant. They are the same on both sides. The only way that this system will work or be equal to each other is if the exponents are equal to each other, because the bases are already equal to each other. Now, this is a nice simple linear equation. Subtract 3 from both sides, and x is equal to -2. Let's just plug this back up into here. -2 plus 3, so that's 2 to the 1 times 4. Yes, that does equal to 8. You must check your work, particularly in exponential equations. These ones are fairly simple, like the ones that we're going to be reducing today. But when we get into more difficult ones that we're going to use another method for, it becomes, sometimes they give us extraneous roots that are solving the equation we have here, but not necessarily the original equation that we dealt with. I'm going to go back to those last ones, but I'm going to spend some time on these because, again, now here, the bases are already the same. They cannot change. The only thing that's going to make these guys different or equal to each other is if the exponents are equal. So if the left side is equal to the right side, the exponents must be equal. So now we have a nice linear equation. We have 2x is equal to 4, x is equal to 2. Plug in 2 back up here. 2 times 2 is 4 plus 3, so 5 and 7 is equal to 5 and 7. Now, here, we don't have quite the same thing. We have 7, and we have 343. Most of us maybe not know that 343 is a value of, or can be written as an exponent 7. I understand that. But 7 cubed, so 49 times 7. So we have taken 343 and written it as a power of 7. That's the reducing bases we talked about earlier. Our bases are the same, so this side is going to be equal to that side. Those guys have to be equal to each other. X is equal to 5. So 7 minus 5 times 2, so 7 to the 3. Okay. Not any different with this one. You have 81, that can be written as 3 to the 4. So we have that reduced down to 3 to the 12x equal to 3 to 5x minus 1. Our bases are now the same. So 5x minus 1 must be equal to 12x. If the left side is equal to the right side, the exponents are the only things that are going to change. So we have -1 is equal to 7x. X is equal to -1/7. Okay. So let's see what happens when we plug this in. We have 3 to the power of -5/7 minus 1, so that's 3 to the power of -12 over 7. And on this side, we have 81 to the power of -3 over 7. If you were to plug those into your equation, they would be equal to, or into your calculator, you would find that they're equal to each other. Yeah, this one's a little bit annoying. Well, that side is going to stay the same. I can write 27 as 3 cubed. I can write the square root of 3 as 3 to the power of 1/2. So we got two guys, same base. Now I'm going to add the exponents together. We have 3 to the power of 3 plus 1/2. So if you want to write it as 3 to the power of 3.5. Or you could write it as 3 to the power of 7/2. Therefore, x must be equal to whichever one of those is written. So, in that case, it was nice. It gave us we had the 3's. Okay, I'm going to try 3. What about 27 and 81? I can't write 81 as a power of 27 without going into fractional exponents. I don't want to do that. But I do recognize that 3 cubed is 27, and 3 to the power of 4 is 81. So we're going to write these guys both as power of 3. So we have 3 cubed, x minus 2, 1 over 3, 4, x plus 3. Now we have a fraction, so let's get rid of that fraction. By writing 3, instead of writing it 3 to the power of 4, I'm going to write it as 3 to the power of negative 4. Okay. So that fraction, that reciprocal can be dealt with by dealing with the negative. Our bases are now the same again. Now we can go ahead and, the only way that this solution, these two sides are equal to each other is the only thing that changes, or the only thing that can change is the exponent. So we have to see which value of those, or what value of x is going to make those equal. Now I've multiplied out, expanded my brackets. I've got 7x on that side, and on that side I have negative 6, so x is equal to negative 6 over 7. Again, should check your work. I don't have a calculator handy on me, so I'm not going to. Fractions kind of do annoy me sometimes. Now, that's our solving exponential equation. Let's just go back to do a review of solving these rational equations here. These are not exponential equations because the variable is the base of the exponent. Now, to solve these guys, what you need to do is get rid of that rational exponent above the variables. And we're going to do that by using reciprocals. So the reciprocal of negative 4/3 is negative 3/4. Why do I do that? When we multiply this out, negative 4 times negative 3 is negative 12. Or sorry, I should say positive 12. 3 times 4 is 12. So what we end up with here is x to the 1. Hey, that's nice. Got rid of my exponent. So if I just our teeter-totter method, what I do to one side, I must do to the other side. We have 81 to the power of negative 3/4. Okay, so again, using our exponential laws, the fourth root of 81 is 3. So I'm going to take that fourth root. I'm going to deal with that fourth root. End up with 3 to the power of negative 3. 3 to the power of 3 is 27. The negative means I have to put it on the bottom. There's your solution, 1 over 27. Same thing with this radical. We cannot do anything with, we don't want to expand this for one thing. We want to get rid of that rational exponent above the variable. Now it's the exact same thing. The reciprocal of 3/2 is 2/3. What I do to one side, I must do to the other. So by raising it to the reciprocal, we're going to get 3x minus 5 to the 1, which I'm not going to bother writing out. So the cube root of 27 is 3 squared. So we have 3x minus 5 is equal to 9. So again, I've taken the cube root of 27 and dealt with it that way. Just again, we can take this guy 27 to the power of 1/3 squared. So I'm dealing with it that way. And from here we have a linear equation. 3x equal to 14, x is equal to 14 thirds. What might be a good idea for you today is to go through and do a couple of the questions, or a couple of questions on the whiteboard work here in the sheets attached. Again, I will be going over these with you, so this is a recommendation that you take a quick look at a couple of those, and I'll go over some of those and give you time to do the homework during class. Have a good evening.